Hello friends, welcome to today's lecture Flexibility Method. Myself, Mr. Y.S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yatram. So in this lecture, we solve a fixed beam problem by using flexibility method. So basically, fixed beam is indeterminate structure because we know the number of equilibrium equation is 3, and for that fixed beam the number of unknowns are 6. For that fixed beam, vertical, horizontal and moment there are 3 reactions for one end. So for that, at end A is 3 and at end B 3, so total 6 reactions. But in this case there is no horizontal load, that's why the reaction at horizontal at A and at B will be 0. So number of moments and reactions at each support is 2, that is at A 2 reactions, at B 2 reactions. So total statical, how to calculate statical indeterminacy is the total number of unknowns minus equilibrium number of equilibrium conditions. So total number of unknowns in this case is 4 and number of equilibrium equation is 2, that is vertical and moment. Means the degree of statical indeterminacy is equal to 4 minus 2, that is 2. So form a matrix of redundant force. Means suppose I want to convert this indeterminate beam to determinate beam. How to convert that beam in determinant? So I can remove this B support. Means now just a cantilever beam fixed at end A and free at end B. So this is the determinant structure. Means I remove that B support. At B there are 2 unknowns, that is vertical RB reaction and moment B, moment at B, that is MB. So this is the matrix of redundant, that is R matrix. The R matrix is RB and MB. Understood? Then next, displacement of analysis of released structure. When I remove support B, now this is a determinant beam and that diagram called as M diagram. Means at support A, that is a fixed support, and B is a free support subjected to UDL 2 kN per meter. Then this is a M diagram, and convert, there are 2 more diagrams, that M1 diagram and M2 diagram. M1 diagram means you just apply a redundant force, that is RB at point B, and M2 diagram is you just applied MB at point B. This is the M1 diagram, this is the M2 diagram. Now form a table. First portion BA, there is only one span, means there is no any portion, just only one portion, that is BA. Origin is B. Now M diagram, suppose I was taking moment about this point B. What is the M diagram or bending moment at B? That is 2 into x by 2, and the direction of the moment is anti-clockwise. Left side anti-clockwise is minus, so minus 2 into x square by 2, so is equal to minus x square. This is the M. Then next goes to M1 diagram. For M1 diagram, now I want taking moment about B, and this due to this force, that is 1 into x. Suppose this reaction moves towards left side, that is 1 into x, and the direction of the moment is clockwise, left side clockwise positive, so 1 into x become x, so M1 is equal to x. Then next, in the M2 diagram, I want to taking moment about B and that subjected to unit load, that is moment at MB. So direction of the moment is anti-clockwise, right side anti-clockwise positive, that is M2 is equal to 1. And limits are, see, the span of this AB beam is 6 meter and origin is B, means 0 to 6. This is the table. This table is useful to find out or to generate flexibility matrix Then next, calculate DRL. So first, DRL1 is equal to M into M1. Means suppose I want to find out L1, you just want to multiply M into M1 dx upon EI. So limits are 0 to 6. So M becomes minus x square. M1 is x. So 0 to integration 0 to 6 minus x square into x dx upon EI. So integration of this minus x cube is x raised to 4 divided by 4, and the limits are 0 to 6. Put up this x upper limit and lower limit, calculate DRL1, that is minus 324 upon EI. Then next, calculate DRL2. DRL2 is equal to integration of M into M2 dx upon EI. We know the value of the M, that is minus x square, and M2 becomes 1. So minus x square into 1 is minus x square dx upon EI. So integration of minus x square becomes minus x cube by 3. Then put up this value, that is 0 to 6 upper limit and lower limit, and solve this equation, that is minus 72 upon EI. So DRL matrix is 1 upon EI is a constant. So 1 upon EI in bracket minus 324 and minus 72. This is the DRL matrix. Now we need to form a flexibility matrix. How to form that flexibility matrix is, this is a 2 by 2 matrix. Means I want to find out F11, F22, and F12 and F21 are both values are same. So you want to calculate 3 values, that is F11, F12 is equal to F21 and F22. So F11 becomes integration of M1 into M1 dx upon EI. That limits are 0 to 6 integration. What is M1 value? That is x into x, that becomes x square into dx upon EI. So solving this equation, we got F11, that is 72 upon EI. Then next, F12 is equal to F21 is equal to integration of M1 into M2, because I want to find out F12 and F21, means indirectly you just want to multiply M1 and M2. Integration of M1 and M2 dx upon EI, limits are 0 to 6. M1 is becomes x, M2 becomes 1. So 1 into x dx upon EI is equal to 1 upon EI, that x square by 2, and the upper limit is 6, lower limit is 0. So by solving this equation, we got 18 upon EI. This is the F12 or F21 value. Then next, F22. For F22 is equal to integration of M2 into M2 dx upon EI is equal to M2 value becomes 1, that is 1 into 1, 1, and integration of 1 is x. So solving this equation, we got 6 upon EI. So this is a flexibility matrix coordinates. So flexibility matrix F is equal to 1 upon EI, F11, F12, F21, F22. So F11 becomes 72, 1 upon EI is a constant term, so take outside of the bracket, that is 72, 18, 18 and 6. This is the flexibility matrix. So that compatibility equation becomes dr is equal to DRL plus F into R. So there are no displacement matrix, so this matrix becomes 0, and the DRL is 1 upon EI minus 324 upon 72 plus 1 upon EI 72, 18, 18, 6 RB and MB. So form a equation, that is simultaneous equation, RB into 72, MB into 18, RB into 18, MB into 6 is equal to that 324 and 72. By solving this equation, we got RB is equal to 6 kilonewton and MB is equal to minus 6 kilonewton meter. So draw a bending moment diagram. Draw a bending moment diagram. Bending moment at B is equal to minus 6 kilonewton meter. Then bending moment at A, that minus 6 plus 6 into 6, that is RB, minus 2 into 6, that is due to this UDL, into 6 by 2, that is become 3, is equal to minus 6 kilonewton meter. And we know the free bending moment for simply supported beam carries a UDL over entire span. The maximum bending moment is WL square by 8. So is equal to 2 into 6 square divided by 8. That value becomes 9 kilonewton meter. Now draw the bending moment diagram. At A, bending moment at A is 6, bending moment at B is 6 and free bending moment is 9. For that free bending moment, join a parabolic line, and that for that negative bending moment or bending moment at support, draw a vertical lines and join. So this is the above the baseline, the bending moment value positive, and below the baseline bending moment is negative, and the overlapping portion is cancelled with each other. There is no effect on this portion. And by using these reactions RA and RB, draw the SFD. The SF at A is 6 kilonewton plus SF at B is 6 kilonewton minus. So join this horizontal inclined straight line, and the line of the shear force diagram cuts with baseline at the half of the span. So this is a solution for beam, that is a fixed beam carrying a over UDL over entire span by using flexibility method. Thank you.